Okay, let's start. We can wait for the another students, but I think we can start without them. And today we will speak. Okay, we will speak. You see this presentation, yes, and we will speak about nonlinear phenomena in nonlinear systems and make some numerical simulation, and then we calculate for nonlinear systems. We find equilibrium points and try to make some simulation in MATLAB. Yes, and I show you the difference between control when we're using the approximate linearization or when we're using exact linearization of the nonlinear systems. Yeah? And you see this this PDF. Yeah. Okay. I hope that you see my screen. Yeah. And the first example is the finite time escape. Yeah, is x dot equal to x2, and we know that the solution is x from t equal to 1 divide 1 minus t. Yes, and I show you on. Okay, I try to share my screen. Yeah, and you see my screen now. Do you see? Yeah. Okay, and we start with this Simulink model. Yeah, this is a simple model, and initial condition 1. Okay, and we can start. And okay, and we can see that this finite time escape. Yeah. Any question here? Okay, and we can try change our model. And this is equal to x dot equal to x is a linear system, and now we can see that this go to infinity exponentially. Yeah, and not there is not finite time escape. Yeah. Okay. The next example is multiply equilibria in one-dimensional systems. The first systems has this form x dot equal to 1 minus x squared x. Yeah. This was just the second one. Yeah, and here the initial condition x 0, 2, and I need this one and selection. Okay. Okay, and now we can see that there are 3 equilibrium points. Yeah, 1, 0, and minus 1. Yeah, and when we start with initial condition 2, it is converged to equilibrium point 1, and so on. This equilibrium point 0 is unstable, I think. Yeah, and this 2, 1, and minus 1 is stable one. Yeah. And I try to. Okay. It's very easy to check. Need to this whiteboard. Sorry, it's some old. Okay. Okay, we have these systems. This system. Okay. This 1, 3. One minus x2x. 1 minus x2x. X dot equal to 1 minus x, yeah, and we need to find the equilibrium point. X equal, first equilibrium point is when x equal to 0, yeah, the first one, 1, x2 equal to, and now we need the another one is when x equal to minus 1 or plus 1, yeah, and this is plus minus 1. Now this x equilibrium point, the second equilibrium point is 1 and the third one is minus 1, and now only you need to check the stability, and let's calculate the Jacobian, sorry, the f x equal to, this is 1 minus 2x2, yeah, and when we put this 0, yeah, here, sorry, when we put here, it's for 0, it's equal to 1, yeah, and eigenvalue is equal to 1, and this equilibrium point, the first equilibrium point is unstable, yeah, the 0 is unstable, and the another two equilibrium points, if x equal to 1 minus 2 plus minus 1 squared, yeah, and it's equal to 1 minus 4, yeah, it's minus 3, yeah, and the second and third equilibrium points, plus and minus 1, is are stable, yeah, because eigenvalue is equal to minus 3, yeah, and it is illustrated here in MATLAB, yeah. And do you have any question? Okay. The next example is x dot equal to minus sinus x, and x 0.3. Sorry, we close this one. This one. Okay, just one for different initial condition. Okay, and you can see that there are many equilibrium points, and this one, this Kp 0, where k is equal to 0 and plus minus 1, plus minus 2, and so on. Yeah, infinity number of equilibrium points here. And okay, and we can check this equilibrium point. Okay. X not equal to minus sinus x, we need to find this equilibrium point, this x dot equal to 0 and minus sinus x equal to 0, and we know that sinus x that x equal to 0 and p 2p and plus minus and so on. Yeah? Okay, and when we calculate the equilibrium, then we can check that this equilibrium point is stable. Yeah? Okay. Okay. On the next slide, you can see the linear oscillator x2 dot plus x equal to 0, or in the normal form is x1 dot equal to x2, x2 dot equal to minus x1. And we know this is linear time invariant system, and the equilibrium point only one, only origin, yeah, 0, 0, and we only show you how this works. Yeah, this linear cycle. Okay, 0 initial condition, 0, 5. And, yeah, and you can see that this linear oscillator is and depend on the initial condition. This is stable, yeah, local stable, and when we change the initial condition like 1, yeah, and sorry, okay, this is this, yeah, and as the same circle, yeah, and we can change here, make it better. Okay, make the tolerance. And now I think it will be better. Yeah. Okay, yeah. It's something like this, but if we add some distribution to this linear oscillator, then is destroy this system. It destroys the oscillation. Yeah. Okay. Do you have any question here? Okay. No question. Okay. The next example is stable nonlinear oscillations. One-dipole oscillator limit circle. Yeah. Let's take the next equation of one-dipole equation. x2 dot minus mu 1 minus x squared x dot plus x equal to 0, where this mu is a scalar parameter indicating the non-linearity and the strength of the damping. Now let's make simulation on the ball. Initial condition 0, and here take minus 3, and we take this parameter mu equal to 3 here, yeah. Okay, and you can see that we start with, I think, -3 here. Yeah, -3, and this is the result. Yeah, we see that when we choose this initial condition, then our oscillation is like this. Yeah. Or for example, here this position. Yeah. We start with -3, yeah, and we have this perfect oscillation. Yeah. And let's try another initial condition, for example, 1. Yeah. Apply. Okay, and we can see that it's the same. Yeah, we start with in 1, yeah, 0, 1, and the figure is the same. Yeah. And we can check. Yeah, we start with 1, and then the oscillation is the same, and we can try to start maybe near 0. Okay, start with I, and run. Yeah, we start here, and we see that this point 0 is unstable. Yeah, because when we start near this equilibrium point, yeah, we go out and stay on this circle. Yeah, and this figure is not depend on initial condition, but it's only depend on this parameter mu equal to 3 here. Yeah, we can choose 1, for example 2, and apply. And you can see that the figure is has the same limit circle. Yeah, and we start here, but it's slightly another figure. Yeah. And do you have any question here with this limit circles? Okay. Another example is double well oscillator, and this is equation 5 is a Duffin equation, x2 dot plus b x dot minus x plus x cubed equal to f cosinus omega t, where b is a damping, f is amplitude of forcing, omega is a frequency of forcing, and let's try a different initial condition in our model. Okay. Yes. I close all these examples, all these models. This DV oscillator. Okay, this is a model, a simulating model of a DV oscillator, and we need to choose this B, F, omega, and okay, let's choose in our let's try it without no forcing. B equal to 0. Try it without forcing, and omega equal to 1. Okay. Sorry. Okay. -3 cosinus f omega omega fb. It's okay. Sorry, I have some problem. Cosinus f omega. Okay, we try maybe with small forcing. B to 0.2 omega to 1, and let's start. Okay. I think I need to change this model because this way for generator. Yeah, it's not cosinus, but now I try to change this. And, cosinus. Okay. Cosinus, and I need to put some time. And this time, and we need to put some this block gain here. Because this is F. Okay, I think now it will be working. Pause. And check. Okay. Pause. Minus. Okay, and try now. Okay, we need to extend maybe -3. This. Okay, we try with f equal to 0. Equal to 0. And okay, and b equal to, and b equal to and 0.5. Okay. Okay, here we can see that we start here, yeah, and in -3,0, and then this system has 3 equilibrium. One is a saddle point here in 0,0, yes, and 2 and 2 focus here, well, 2 stable point, yeah, here one and here one, on -1, -1 and 1, yeah, and when we start, the trajectory converges to one of equilibrium points. Okay, and let's change the initial condition. Let's add some small forcing. This be 0.25 and f equal this force 0.22, and omega has the same 1. Let's try simulation. And okay, we change this. Try with here is 0. Okay, 1, only 1. And let's try to simulate. Okay, and now we can see with a small forcing and start here in 1, yeah, and we can see that there's some stable limit cycle here, yeah, and maybe 2, the another one, on this figure we can see that there are 2 limit cycle inside. Yeah, we start here and then we stay on this cycle. Yeah, and now we can. Do you have any question? No? Okay. And now we can change forcing. Yeah. Make bigger forcing. And 0.25. Okay, and no, f equal to 0.2. It will be better, and And now start simulation. And we can see that some climate cycle. Yeah, this one, no. Maybe another one. No. But you can see that it is different, yeah, because this we start in one, yeah, and then this oscillate near the equilibrium point 1, and then it's go down, yeah, in 0 it's unstable point, yeah, and go to another stable, to another equilibrium point, and oscillate near the second equilibrium point, the third equilibrium point -1, yeah, and then it's go and go up, yeah, and here it's unstable point, and go up and oscillate near the stable point, yeah, the another stable point. And yeah, you can see that this oscillate here, we start and go, and then go to another and oscillate around another equilibrium point, and then come back, yeah, and oscillate around this equilibrium point. And this transfer is complicated and resembles chaos, and basin of attraction have complicated boundary. Small change of initial condition may lead to a different climate cycle, and the boundaries have fractal character. We can try to change the initial condition, only initial condition, yeah, and okay, try to change. We take not one, but for example, very close number, 0.9. Okay, and now run the simulation with the same parameter forcing and B, yeah, and now you can see that it is quite different, yeah, and it starts here, yeah, and its rotation around this equilibrium, 0, 1, yeah, and then jump to another equilibrium and rotate around this point, yeah, this position, yeah, this start and rotate, go down and rotate. Do you have any question here? Okay, and try to change this initial condition. Let's change to another one. For example, 0, 1. Okay. Run. And yeah, you can see that it stay only, it's rotate only around this equilibrium point, yeah, not jump to, yeah, it's rotate this, and we can try to make maybe more time, and try, and not make the same, and you can see that position is the same, yeah, it stay around this equilibrium point 1, yeah. Any question? Okay. Maybe try change. 100, and here not only quite smaller. Okay, and 1. Yeah, and now it's jump. Yeah, in jump and rotate several times and come back to this first, and you can see this on this position. Yeah, start with 1, near 1, and we change only add not 1 but 1.005. Yeah, and now it's quite different. Okay, and it's you can see that behavior of the nonlinear system depend on initial condition, yeah? Not only on the force parameter or parameter B, but on parameter on initial conditions. And let's change our parameter F and even more forcing 0.4, yeah, and omega equal to 1 and B equal to 0.25, yeah, and it's in the same. And now we run and sorry, and here you can see that it's quite chaotic. Yeah, this is chaotic behavior. Maybe we can change this initial condition to 1, for example. Only 1. Let's start, and you can see that it's we start with 1, and it's oscillate around this first equilibrium point and then jump to another, and only once go around this equilibrium point and come back. Yeah, but for example here it's 2, yeah, 2 times oscillate, here only 1 times, and so on. Yeah, we can time, expand time, and we can see that, yeah, perfect behavior, this chaotic behavior, yeah, and unpredictable behavior. Do you have any question here? This is example of chaos, yeah, because we can change a small change of initial condition, and we can't predict, yeah, the behavior of this system. Okay, if you have a question, we can try to, maybe, I think no more time, no, but try this initial condition change 0.1. Okay, and the state plot rate is this figure, yeah. Okay. Do you have any question or maybe some remark? No. Okay. Let's see. Okay, we try different initial condition here, yeah, and okay, now buckle beam bifurcation. Okay. The next equation is a equation of buckled beam m x2 dot plus dx dot minus mu x plus lambda x plus x cubed equal to 0. D is a damping, mu is a load, and this term is a elasticity of beam. And we can rewrite this system in a normal form. Yeah, let's find the equilibrium points, and then let's to analyze them based on the signal of the term mu minus lambda. Okay. One moment. Okay, buckled beam. I hope that it works. Yeah. Okay, it's not buckled beam, but it's not buckled beam, and I think we can change our model. Now I change this model to this buckled beam. Okay, this is x1 and this is b. It's not b. x3. Okay, x1. We need to add some. Okay, this is not b, but x1. Again, some mu, some K2, for example, K2, and this K2 equal to mu minus lambda divide m, and this is not b, but some K1 is d divide m. Okay, this one is K2 is mu minus lambda m. Okay, and the last one. Okay. Okay. Something like this. This is K3. K3 equal to 2, 1. Okay, this is this. Okay. Okay, now it's. I think it will be works, and only define this K1. Okay, and Okay. Okay. For example, 3 lambda equal to 1. Sorry, 1 and mu equal to 0.8. Okay, mu lambda. Okay, and m. Yeah, and now we need to calculate this. Okay, 1 equal to okay, 1 is equal to d divide m mu minus lambda divide m and 3 equal to 1 divided m. Okay, and now okay, now this is buckled beam. Run the simulation, and it's not so interesting. And let's try another initial condition like 3 and run. Okay, 3 and minus 4, for example. 3 and minus 4. Okay, you can see that it's converged to 0, yeah, to equilibrium point 0, and this one we start here, yeah, and go to equilibrium point 0, 0, yeah, and let's change d lambda, already know, but only lambda and mu, and now we change lambda equal to 1 and mu greater than lambda equal to 3, mu equal to 3. This one and this one, yeah. Because d is the same, yeah, d equal to 0.3, and we only change mu, yeah. And now we start the simulation. Okay, we can see that it's converged to not to 0, and it's not converged to 0 now. It's converged to some another equilibrium point, yeah. And this point is, we can calculate this point if you want, and some old graph. It's okay. I need to maybe more 6. Maybe. Minus 10. Okay, and start it again. okay, position velocity, velocity go to 0, and the position go to this equilibrium point. This equilibrium point not 0. And, okay, you can see that we start here, and then we go to this equilibrium point. Let's try another initial condition. For example, you can see that this one equilibrium point, I think here it's this saddle point, unstable point, and here it's another one, and we can try to choose another initial condition, and then okay, this is 0, for example, and here it's something like 0. It's near to 0, and run. Okay, you can see that it's go to another equilibrium point, because here now we start near the unstable equilibrium point. Here it is a saddle point, and go to equilibrium point, the second, and another one here, and now you can see that it is there are two solutions, there are two equilibrium points when mu greater than lambda, and we can show it with calculation Jacobian, for example, and found this equilibrium point. This is 3 equilibrium point, and okay, let's try just another, not 0, but for example 1, and start. And now we start here, and make one rotation and go to another equilibrium point, this is phenomenon is called bifurcation, because when we change some parameter in our equation, then the solution changed. When for example here, when mu less than lambda, then only one solution, it's 0, and 0 it is equilibrium point, stable equilibrium point, and then when lambda equal to mu, the solution is the same, equilibrium point 0, but if mu greater than lambda, for example, we can try another mu not equal to 3, but for example equal to 1.1, and we can try to change this mu equal to 1.1, and we recalculate this second K2, and now we start, and you can see that, okay, this goes outside, okay, not outside, but you can see that now equilibrium point is equal to 10, one equilibrium point equal to 10, but another one equal to -10, we can start not near, for example, we start near -5, I think, and then run, and you can see that, Let's go to another side, yeah, and here it's equilibrium point -10. Yeah, you can. 12. Okay, let's start, and you can see that. Yeah, it's the same. We start here, yeah, go here, and this equilibrium point is stable, and we stay in this stable equilibrium point. And the position is start with -5 and go to -10, yeah, and stay in -10, because -10, 0 -10 is the third stable equilibrium point. Do you have any question here or some comment? Okay. If I choose here 0 and here 0, yeah, can you predict the behavior of the system if we start with initial condition 0 and 0 here? Can someone predict? It's a question, yeah, for all. Let's try. Okay, I want to ask Philip Novak, if you know, when I choose the initial condition 0, 0. Okay. I try 0, 0, and you can see that velocity is 0, and the position is the same, 0, because 0, 0 is unstable equilibrium point, but if we start with this initial condition, we stay in 0 infinity long, because you can see that all this term, it's this term x, and x dot equal to, for example, here, this x2 and x2, x1, x1 equal to 0, and then it's not velocity, and we stay in this equilibrium point. But when we choose only make small change of initial conditions, then we go to another equilibrium point, stable equilibrium point. It's 0, 10. Any question? Okay. The next some example from Khalil book. You can try it at home. This exercise 210. And try to find the equilibrium points and determine their tips when b1 greater than 1. And note that e greater than or equal to 0. And repeat this part when b1 less than 1, and you can try to construct the phase portrait of the system for this parameters. Yeah, you can try to construct and repeat this with only change this v1 in 3 in question 3 it's equal to 1.5, but in question 4 it's only changed this v1. Yeah, and we can construct it now, but I think it's not so interesting. And the another it's Hollywood motivational model of the pendulum. Yeah, and we can do it, but I think it's very similar with example from first classes. Yeah, and okay, now I try to show you the control design of the linear system based on the approximate and exact linearization. Yeah, and try to stabilize the next nonlinear model described by the next equation. Is x dot equal to ax cubed and plus control u. Yeah, where x and u in R and a parameter a greater than 0. Yeah, and okay, I run this whiteboard. Yeah, and show you how we can do it. Okay, x. Okay, try here. Oh, if I want to. Sorry. Okay. Okay, x dot equal to ax cubed plus u, and x u in R, and parameter a returns 0. Yeah, and we know that this system is unstable. This part is unstable when a greater than 0 and stable if a lesser than 0. And we can make a linearization of this equation x dot equal to 0. Yeah, because when we linearize this part, yeah, only 0 here. Yeah, and then x dot equal to u, yeah, because here only u, and x dot equal to u, and then we can stabilize this system by the control u equal to minus k x, yeah, where k greater than 0. Yeah, do you have any question here? Okay, any question? Okay, and we know that this control law is when we put to this, to this equation and put here, then this approximate linearization of our nonlinear system is asymptotically stable. Yeah, and but when we put this control to our equation, to our original equation, x dot equal to a x cubed minus kx, yeah, and let's find the equilibrium point of this nonlinear system, and we can write this x dot equal to x, and here it's ax bit minus k, yeah, and we can see that the first one x equal to 0, yeah, when x equal to 0, then x dot equal to 0, yeah, and the other one, it's this a x cubed minus x, sorry, minus k, yeah, and it's equal to 0, yeah, and the a x cubed equal to k, and x1, 2 equal to plus minus k divide a, yeah, and okay, and let to analyze the equilibrium point of this system, yeah, the stability of equilibrium points, and I can show you that we can use the function here, the function v. Yeah. It's from the last slide of the lecture. This function v is the so-called Lyapunov function. For example, take function v from x cubed, yeah, and the time derivation of x equal to 2x dot, yeah, and it's equal to 2x, and this, yeah, and this one, a x cubed minus kx, yeah, and this equal to minus 2x cubed k minus ax squared, and we can see that this the derivation of Lyapunov function is negative on the next interval from minus k a x and k a, yeah, this root, yeah, this is this negative, this one, yeah, and this negative, and if and positive if x greater than k a, yeah, the module, the absolute value of x greater than this root of k divide a, yeah, and for and we can see that if this derivation of the Lyapunov function is negative, then this on this interval, this system is asymptotically stable, yeah. And do you have any question here? Okay, and I start MATLAB. And approximate linearization. This is the example, yeah. And x, okay, x0 and on. Sorry. Yes. This one, yeah, and run. And now we can see that if we start inside, because here I choose some k equal to -1, yeah, k equal to 1, yeah, k equal to 1, and a equal to 1, yeah. And when I choose this parameter, then it's a symmetrical stable from -1 if x greater than -1 and less than 1, yes. And you can see that if we start with initial condition inside, yeah, with x0 inside this, yeah, then we converge to 0, yeah, to equilibrium point 0. But when we start outside of this interval, because our initial condition, for example, here you can see that -1, it's x. Okay. I choose -1.00001, yeah, -1, and so on. When we start with -1, or with this first or this third, with the second initial condition, then you can see that if we start with -1, this is unstable equilibrium point, and this stay on this in this equilibrium point, yeah. But when we start outside of this interval, then we go outside, yeah. But when we start in this interval, -1, 1, yeah, inside, yeah, it's converged to 0, yeah, to our equilibrium point 0. And okay, in this example, our linear, sorry, in this example, this our linearizable, our model, which is approximately linearizable, yeah, then it's x dot equal to u, and we design this u, and this u for this linear model, it's a global is global stable, yeah. But when we put this control to our nonlinear model, yeah, then you can see that it's stabilized only on some interval, yeah, only on this interval when x greater than minus root k divide a and less than root k divide a, yeah. Do you have any question here? Okay, you understand all this. Okay, and now we can try to make linearization via feedback. Okay. The exact linearization, the same, x dot equal to ax cubed plus u x u r and a greater than 0. And now we choose x dot equal to ax cubed plus v, yeah, not v but o. Okay, sorry. Okay, we take u as we cancel this term, yeah, minus a x cubed, and then minus kx, yeah. Or we can say that it's plus v and v equal to minus kx, yeah. And then when we put this control u to our original system, then x dot equal to ax cubed plus, and this u minus ax cubed minus x, it's all equal to these terms cancel, and it's all minus kx, yeah. And now we can stabilize our system with this control, yeah. And I can show you in simulation exact minimization is okay. I need to choose some a. Okay, we can take a like no 1 for simplicity, and 1, yeah, and this initial condition. Okay, we take many initial condition. This minus 10, minus 5, minus 1, 1, 5, 10, and we can end another one, for example 100, yeah. Evaluate. Okay, and now we start the simulation. Okay, and you can see that will stabilize our neural system with this kind of feedback, yeah, control. And I can maybe try more time, and yeah, you can see that we start with different initial condition and go to 0, yeah. And and this control guarantee the symmetrical stability of the system globally. Yeah? Do you have any question here? You hear me?
Yes, we do hear you.
Okay. And you have a question, yeah? About the stabilization, about this. Okay. And now we have some time and we can to solve some example. Okay, for example, we take another now this is x1 dot equal to x2 and x2 dot equal to x1 minus 2 arctangents x1 plus x2. Yeah? And let's construct the first portrait and discuss the qualitative behavior of the system. Yeah. And we need to find the equilibrium point, and this equal to 0, yeah, and equal to 0, yeah, and then we can find and x2 equal to 0 from this, yeah, from this part, and now put this x2 equal to 0 and x1 minus 2 minus 1 and x2 equal to 0 x1, yeah. Okay, and now we need this equal to 0, yeah? And what's the solution? This part. Okay. But we know that if okay, here it's when we solve this question, we found that the equilibrium point is the first one is 0, 0, yeah, and the second one is A0 and this and minus A0, yeah, because x1 minus equal to 2 times x1, yeah, and how we can use in the MATLAB, yeah, and to find the equilibrium points, and we can plot this x and this x. Okay. Okay, we can plot this. Okay, because here the next step is x1 divide 2 equals to tan minus 1 x1. Yeah, and when we plot this in MATLAB, yeah, these two curves, x and tangents x divide 2. Yeah, we can find this equilibrium point. This A is like 2. It's like, yeah, is 2, 3. Okay. 2, 3. Yeah. Okay. And you can find that this A is 2, 3, 3. Yeah, and okay, and now we can find the Jacobian, calculate the Jacobian, 0, 1, and just here you can see that this x2, this 1, and 0, 1, and here it's this is 1 minus, and we need to, well, the derivation of tangents is equal to 1 divided 3. Okay, minus 1 plus this x1 plus x2 squared. Yeah, and sorry, this one here 1, and the second one is minus 2, and 1 plus x1 plus x2. Yeah. Okay. This Jacobian. Let's find Jacobian in 0. X in 0 is equal to 0, 1. And here it's 1 minus 2 divide 1. Yeah, and here minus 2 divide 1, 0, 1, and minus 1, and here minus 2. Yeah? And let's find the eigenvalues. It's minus lambda, minus 2 minus lambda, minus 1, 1. It's equal to lambda squared plus 2 lambda and plus 1. Yeah, and as we know, this is stable because all coefficient near the polynomial is are positive, yeah, and on the 1, 2 equal to only for control, minus b minus 2 plus minus minus 2 plus 2, and here it's like 4 minus 4, 1 is equal to minus 1. Yeah. Okay, this the equilibrium point 0, 0 is stable. Yeah, it's stable node because eigenvalue is equal to minus 1, both eigenvalues, yeah, because this part. And the another one, okay, I see we need to finish, yeah, because time, and you can calculate at home, say another 2 equilibrium points, yeah, and do you have any question? Do you have any question about the homework? Yes. No, only real equilibrium, yeah. You don't need check some complex because, for example, many systems is a physical, yeah, and you need to check only real equilibrium, yeah. Hmm? Any other question? Another question? Okay, thank you very much, and see you next week. If you have any question, you can write me a mail and ask. Yeah. Goodbye.